my smartphone working. For me, my smartphone was working the other day. I don't know why it turned off yours also. Anyway, let us start. Okay, let's go to cell induction today. Okay, we still got energy and we still got mutual induction. Okay, that's your value of constant. You must know where to find what you want. Part of it only, I'll cut for you part of it or copy for you part of it. Okay, so all these things you must know. Flux, what is flux? What is flux linkage? Lenz's law, Fleming's right-hand rule. Right? Lenz's law is conservation of energy. Faraday's law. And then in mathematical form, we have basically we are just using Faraday's and Lenz's law throughout all these that you are going to learn. And then know that for a linear conductor, your EMF induced in the conductor is PLV. Okay, so as far as self-induction is concerned, supposed to be 5 hours. Explain the phenomenon of self-induction and define self-induction.
Wait, the other some topic takes long, is it? Yeah.
This topic will take 5 hours according to what the ministry required. Okay? So I'm not going to go that fast. Use the formula. Right? We'll use this formula. We'll derive this formula. And then we will derive the formula L for self-induction, or we call it self-inductance, L. Okay, let's go into self-induction. Self-induction is the phenomenon in which an EMF is induced in a conductor when the current in the conductor changes. Right? Phenomenon is what is observed. EMF is induced. That's the key. EMF is induced. Current in conductor changes. So when you, this is a symbol for switch. Right? You close your switch, the current will flow. Remember the current, the electron take time to move. So the current will start to increase. So the current is the one that produces a magnetic field, and the magnetic field is the one that produces a magnetic flux. So the flux is changing across the conductor or the coil itself. So you have induced EMF. That's what it means. Okay. So that is your Faraday's law, which we are just applying. Right? We can replace our phi with PAN. Right? P is contributed by this coil, this solenoid. A is the cross-sectional area, this cross-sectional area. N is the number of turns of the solenoid. And then remember, if it's a solenoid, this is your mu naught, this is your small n, this is I. What is small n? What is the symbol for small? What does small n represent? Yep, Srini, what does small n represent?
Small n, number of magnetic flux linkage.
Okay.
Number of turns.
Number of turns per unit length.
Yes.
Okay, so that is basically tell you the current is the one that causes the induced EMF. Right? No current, no flux change in the solenoid. As the switch is closed, current increases. Right? There's a current. There's a positive terminal of the battery. There's a current. Magnetic flux linkage. Magnetic flux linking the solenoid increases. So current increases, the flux increases. That's what it's saying. And then if the flux is increasing, here is your EMF is induced the solenoid. And if EMF is induced, you will also have a induced current that opposes the direct current. So that is your induced current. You oppose the direct current. That's why the direct current doesn't rise instantly. Right? We call the induced EMF back EMF because it opposes this one. This is a direct EMF. It opposes the direct EMF or the battery. So that's why we call it back EMF. Right? That's the direction. Same as the induced current. Back EMF is proportional to the rate of change in current. Right? Back EMF is proportional to the rate of change of current. And then there's a constant L there. Negative because of Lenz's law. And L because cell inductance. Negative sign means that the back EMF opposes the direct current. Right? Lenz's law. Okay, so usually we are more interested in solenoid rather than coil, but sometimes the author will mix it up. Coil and solenoid are the same thing. Okay, that's your Faraday's law. Right? I'm just showing you that there's a need for us to define a new term. That's all. Right? So we have our BAN. We replace that flux linkage with BAN. That's all. Your A is constant. Your N is constant. Your B is the one changing because the current is changing. So B is changing. So now we have dB dt. Then remember our B, we can replace it with mu naught and I. So replace that B with your mu naught and I. Right? Remember your N is constant, your mu naught is constant. So for solenoid, N turns and length L. So now I'm replacing that mu naught is there. And the fifth sign is there. That N is just N divided by L. And that's your AN. That's your AN. And then what's left is I. So it's di dt. Okay. So we can see that this is a constant, mu naught and LAN. Right? I rewrite that here. It's a constant of the solenoid. It doesn't change as long as the solenoid is the same. Right? It depends on number of turns and depends on L. The thing that changes is E, induced EMF, and the rate of change in current. So that's why you see that we need to define a new term. Right? We change di dt to obtain E. So we need to define a new quantity, E divided by di dt. That's the reason why we define L, cell inductance. Definition of cell inductance. Cell inductance of a conductor, right, represented with L, is the back EMF, right? Back EMF divided by di dt. We won't bother about negative sign because it's a magnitude. It has a value. Don't bother about negative sign. Right? That's why in formula form, we're just using this formula, that's all. E back di dt. Right? This one is the induced current. L is measured in Henry. So 1 Henry, right? If the inductance or conductor is 1 Henry, then the back EMF is 1 volt, and the current is changing 1 ampere per second. So changing already, we finally will increase to a stable current. How do we find a stable current? Stable current, we just take the voltage supply V or the applied voltage divided by R. R is the resistance of the coil. The coil will have resistance. Anything will have resistance as long as it's a conductor. Okay, usually we just assume it's 0, but it has a resistance, the coil. Resistance of coil, R. Any comments so far? So if we look at the rise of current, it's actually exponential. We are not going into the math involved, right? Not too much detail, but it's actually a curve, exponential curve. The current is increasing until it's finally constant. Depend on same as what we learned in your capacitor, charging a capacitor. There's a time constant there. Same here. You also have a time constant. L divided by R. But as I said, you don't need to know that detail. Just know that the current is increasing until finally it's constant. I equals to 0, that's the point. Right? Not back EMF, not induced current, not back EMF. Right? This one is 0, doesn't change, not back EMF. Final current, know how to derive, V over R. Current rises exponentially when the switch is closed, di dt. Right? Remember, di dt is the slope there. The slope there is very steep, changes very fast. That means 0 to something is a change already. And then you can see the slope become less and less. So di dt becomes smaller and smaller. Initially, greater slope, slope become less and less. And then finally, as it reaches a constant current, the slope is 0. Right? Yeah, so back EMF is proportional to di dt. Di dt is just the slope. Right? So back EMF decreases as current rises or current increases, and 0 when the coil reaches the final current. At this part, no back EMF anymore. The current doesn't change. Field doesn't change anymore. Okay, so when the switch is open, this is where the switch is closed. There's the induced, there's the increasing direct current. There's the opposing induced EMF. Now what happens when we increase when we open the switch? When the switch is open, this current, that current, you switch it off, the current is going to start decreasing exponentially to 0. So we know that induced EMF or back EMF is large. Try to support this current, to keep this current going. That's why you see that induced EMF is the same direction as the current that is decreasing. Right? When the current want to increase, it opposite. When current want to go to 0, it try to help it. So that is the current across it. That is the current across the, initially it rises, the switch is closed, and the switch is open, the current also decreases. That's how the graph looks like. Switch is closed, it rises, and after that, constant current, and switch open, it decreases. Right? Remember, the IDT is the slope, the gradient, and back EMF is proportional to the slope or the gradient. Back EMF decreases fast initially, this part there, decreases fast initially, the slope. Right? So we can see that is your back EMF, it decreases very fast initially. After that, it starts to decrease to 0, where the current is constant. Okay, so that is the representation. Right? There's less turn, there's more turn, there's a coil or inductor. Right? Inductor application, generally, inductor is used to delay the build up current inside. Right? It takes time for the current to build up, so it delays the current reaching the final value. Sometimes inductor is also called a choke. Right? We are not interested in this one. This one is for rectification. In DC circuit, it is used to prevent the motor from being overloaded. You don't want the current to rise up too fast. You want it to slowly. Inductor and solenoid. An inductor is a coil of wire worn on the center core. Right? Center core can be air or can be iron. And it's used to provide resistance to DC current flowing through the wire. As a solenoid is a type, basically it's an electromagnet. Right? Type of electromagnet, purpose to generate and control the electric field. Right? So we do use inductor, right, which is a solenoid. Very small. You use it in the circuit. Inductor and resistor in series. Current through an inductor. Okay, so let's look at this circuit. There's your A, where you open the switch. B, where you close the switch. C is where you remove the battery. Okay, let's see what is going to happen. When the switch is closed, we move from A to B. The current in the circuit rises as we have studied before. You close the switch, the current will start to rise. We call it exponentially to the final current. Final current, there's a final current determined by E, that's your power supply, divided by R. Right? R is the resistance of the circuit. There can be this resistance plus the resistance of the solenoid. E is the supply voltage. When the switch is at C, remember it's not open, it is connected, the current still can flow. Right? So this one show you the supply current. Initially at A, open, no current. When you close point B, current rises to final value. And then when you close the switch to the other side, basically do the same thing as what we did just now. Right? This one is just clear, showing that it must have closed path before the current will decrease exponentially. Right? Voltage across an inductor. As the switch is closed, because of back EMF is large. You can see that back EMF is large. Due to the rising current, the voltage appear across the inductor. No voltage across here. When you close the switch, allow back EMF is across here. As the current becomes constant, doesn't change anymore, so no back EMF. So that's why voltage is now across the inductor is zero. Across here is zero now. It appear across here now. Right? No more here. If there is no resistance in the inductor. When the switch is at C, this part, the current decreases exponentially. The voltage across the inductor changes direction. Right? The EMF is different direction now. Trying to maintain the current. Right? Trying to keep the current going. That's why it's opposite direction. Okay, try this question.
So go back.
Yeah, what's the problem? Any problem? Basically, this one tell you is the back EMF is large. Right? If no current flow, there's no voltage here. Most of the voltage is across here. That's why you have that. Then when the induced EMF or the current is constant or induced EMF here, the current is flowing through here. Right? This graph is just for here, for the inductor.
Okay.
Okay, try this question. Basically, using the formula I've just gone define for you. When the current in a solenoid decreases from 25 to 0 in 20 milliseconds, the induced EMF is 4 volt. What is the self-inductance of the coil? What is the answer? Ken? Just use that formula. Don't bother about the negative sign. What is the answer for L? Ken? DIDT can take it
500.
cross multiply that. Where EMF is 4. Delta I, that's a delta I, by 5. This one changes to second. Okay. Nope. Where is your mistake?
Oh,
careless again.
Yeah, actually it's 25 divide 0.02, right?
Yeah.
And then I times with 4.
Okay, carelessness. Cannot must avoid carelessness. Okay, now we are going to derive this, show that Li is just equals to flux linkage. Where EMF, that's a formula that we have obtained. You can do it experimentally or you can show it. Then we compare with Faraday's law. Okay, take this L to the top there, it becomes Li. Then we compare these two equations. Right? Compare the two equations, we got Li equals to 5. Okay with that?
Okay.
Just memorize and know how to use it. That's all.
So just memorize and you know it to understand.
No, it's understanding now. I show you already. How do we derive it? Compare these two formula. Basically, this formula is derived from here. I've shown you earlier. Derived from here. So you can expect that your 5 equals to Li.
card.
Just know how to use the formula. So inductance of a solenoid. Suppose the solenoid has a length L and number of turns per unit length. Number of turns per unit length is N. The magnetic flux density for current I, right? That's your formula you need to remember for solenoid. Then replace that N with NL. Right? Earlier I've derived for you already from Faraday's law. Now I'm just deriving it using our new law, where EMF equals to L di dt. Right? Flux linkage. Flux linkage BAN. So your B, A, N, right? B I replace with mu naught. That's a mu naught. A is still the same. There's a N, L here. There's an N here, so it's N squared over L, and then there's an I there. Okay. So now I just derive for you that equation. I can compare these two. Right? 5 flux linkage, There's your I, there's your I. So now I can get my L. Mu naught A N squared over L. Okay. Usually they will ask you to derive. But you need to remember the formula and know how to use it. Okay with that? Any comment? Anything not clear?
Oh, so there's Li equals to magnetic flux, then you get the answer already lah.
Yeah. We have derived earlier. Right? We have derived earlier if you've forgotten. We have derived earlier. I just show you a different way of doing the same thing. Where is it here? Yeah, we can use Faraday's law directly. Yeah, we use Faraday's law directly. We get the same equation. There's your L. Right? It's just that here we have to define the term. E di dt is L, that's all. That's what we are doing. Right? Or you know, you can use Faraday's law to derive directly. Same thing, the same formula we get. Okay, since we have got a lot of equation, 3 or 4 equation, now it's time for you to solve the equation, solve some problem. Okay, remember that formula? Try this, solve this equation. A wire carries a current of 160 milliampere. Remember to change it to ampere. The magnetic flux produced by the current is 0.8 Weber. What is the cell inductance of the loop? Getting you to use the formula I've given you. What is your answer for L? Then use that formula, that's all, that we have derived. And calculate your L. Right? Path linkage divided by current. Put in your value. Use your calculator. Should be able to get 5 Henry. Can or not?
Can.
Okay, good. Oops, try another one. Yeah, didn't remove the. Try the question without looking at the answer. Okay, try this one. An ideal solenoid consists of 500 turns of wire per cm wound around an air-filled cylindrical core. The solenoid has a cross-sectional area of 1.6 cm square. Remember to change to meter square. And 2.4 cm long. Remember to change to meter. A current of 2.5 ampere passes through the coil. Calculate the magnetic flux in the solenoid. Right? And to calculate B. Sorry, 5. Yeah. It's now straightforward. This one a bit more challenging. What formula to use? Yeah, start with that. Since they have given you your N, your I, you not have to go to formula sheet. Put in your value. Yeah, can.
Yeah, can.
Right? That's your flux, BAN. You calculate your B. A, change the meter. Right? That's your A. 1.6 change to meter square. Your N is 500. Sorry, did you find any mistake that I made? Did you find any mistake that I made?
No.
What's your
I don't
answer?
know, sir.
What's the answer? What's your answer? I make a careless mistake. Right? This is 500 is 100 turns per cm. Okay, turn per cm. So I have to multiply by 2.4. Right? Since this is per cm, this is 2.4. I just multiply by 2.4. Right? The cm and cm will go off. It becomes number of turns. Sorry, didn't realize the mistake. Let's pick it up. Okay, so after that is the calculation same as before. So it's point. Okay, you have to change the new zoom soon. 0, 5, 2, 4 times 2, 5, 4. Okay, so I should get 0, 1, 2, 5. One, two, 1, 2, 6. Okay, so I've changed here, I have to change here. One, two, 6. Divide by the current is 2.5. Divide by 2.5. Okay, so I get 503. 503 millihenry. Okay, any comment?
No, teacher.
Okay, I think it's good time to start a new Zoom. But before I start a new Zoom, these are the questions I want you to try out. Okay, the 5 minutes break. If you want, you can take the break. If not, you can try the question. Your book, page 220 to 227, 5, 14, 16, 17. And then we'll try one structure one. Okay, so we'll stop here. 5 minutes break.